So typically, the higher return loss, the better, has less reflection. So if you have a 20 dB or device with a 20 dB return loss, you're getting transmitted power of 99%, and only 1% of the power is actually reflected. If a device has a return loss of 5 dB, you're getting 31% of power that's reflected. Only 68.4% of the power is actually going into the device. So a higher return loss is actually better. We could also show this visually a little bit too. So you have a device here that has 20 dB return loss of signal going in. If I have an input power going into the device of plus 35 dBmB, for a 20 dB device, the actual reflected power is the difference between the two. And the power reflected is actually 15 dBmB reflected. So, even if you have products of a spec with good return loss, there are many things that affect the return loss, like you mentioned before, impairments. So a simple, bad connector, squirrel chew, and these things are all normal in the network, or they're supposed to 75 ohms. You could have unterminated ports. So if you have a device here and one port doesn't have a 75 ohm connected to it, you could affect the return loss on all the other ports if one of the ports is not terminated. So those are all things that could affect return loss in the network.
What would be a good figure for return loss for a passive, Neil?
So typical passives we use in the industry is like 16 dB or better for return loss. And going back to this slide, that is about more than 97% of the power transmitted into the device. So that's a number that's been used in the industry for quite a while. But you can use things down to as low as 12 or 13 dB. It's really depending on your network design and what type of modulation is required and the reflections that's associated with it. For example, FDX may have a higher requirement for return loss, especially on taps that are closer to the node. More reflection occurs there. So those type of taps may have a return loss requirement of something you may want better than 20 dB. But low value taps or other networks that have lower requirements for return loss could have something, 15 dB or so, or even lower. I've seen products specified down as low as 12 dB in the satellite network and satellite systems.
Now, something you mentioned there that piqued my interest. We've typically thought about return loss on the downstream, right? Because of the amount of power or amplitude has historically been higher on the downstream in these sub-split systems, right?
Right.
Well, in the DOCSIS 4 world with high split, ultra high split, FDX, now we're going to see more power also on the upstream than we've ever seen before, right? So managing reflections and having really good passives with good return loss figures is going to be more important than ever.
Right. And as new products are being introduced, I see the industry, and that's where vendor differentiation occurs. You could see return losses getting higher and higher, looking for better bands. So you can have certain return loss in your FDX frequency band that may have a better return loss than certain frequency bands that don't require that return loss. So you could tune and match your product to have increased return loss where needed for that specific application. But yeah, upstream is definitely with the amount of power being put into the device, this is being a big requirement these days.
All right, so we've come to the conclusion that return loss as measured at a device is a different value than the return path loss or upstream path loss from a device to the CMTS. And in this instance, the return loss of a device, higher is better, which means less reflected power.
Correct.
Got it.
Okay. I think we're going to go into mainline passives next. These include splitters, directional couplers, power inserters, and inline equalizers. So we'll talk about each of these mainline passives.
All right.
So mainline passives are all non-active devices on the hardline coax. This includes two-way splitters, three-way splitters, balanced and unbalanced, and we'll explain what that means. Directional couplers, and we'll talk about how they work. Power inserters and line equalizers. Multi-taps are passives, but when people say line passives, they typically mean the devices above. Multi-taps usually are categorized as tapped itself. So this section here is on line passives, and we'll talk about these products here. First is a two-way splitter. This is pretty self-explanatory. Equally splits the RF signal between one input to two outputs. It is bidirectional, so it's not just a splitter, it's also a combiner. So signals can come in through the out and combined at the input as well. So each port passes RF, but I'm going to show the AC path. There's also AC that goes through each of the ports as well. So the red dotted line is where AC goes, and the blue line is where RF goes. You can actually activate or deactivate AC going down each of the lines of the ports independently. So there's a fuse or an AC shunt bar on each of these ports. Line passes are typically shipped with these AC fuses pre-installed, but based on network design, if you remove one, you can save power if there's no active devices going out, let's say this leg. Then you can remove the fuse from this location and there's no AC going down that leg. So they're configurable where AC can go down all or none of the ports. The fuses are user, and a technician would remove the fuse from the device.
So can we talk real quick about how that works, Neil? Because
yes.
AC is also a wave like RF, right? But it's a much, much lower frequency wave of 50 or 60 hertz. So
yes.
The routing of RF and AC is really just done with diplex filters. Is that right? We're separating frequencies.
Yeah. So a diplex filter is a device that combines or separates frequencies. So that is what's actually inside each of the products. There are filtering parameters so that the AC at the low frequency in 60 hertz goes through the red line, and 5 megahertz goes through the blue line. So there are diplexing components in here that split the frequency into the correct paths that requires to go down.
Yeah, that's one of those things that it took me a little bit when I was a new technician to kind of get my head around that RF and AC were both waves of different frequencies. And that's why they coexist so well in our systems when they're combined and decombined and managed in different places in the network.
Yeah, and they're both traveling down the same coax. The way I like to look at it is your FM radio, and I like to explain it that way many times, where you can have in the air all these frequencies transmitting data, but your radio is actually tuning into one of those frequencies to pick out that radio station you're looking to. Similar to coax. The coax there has all the frequencies in there. Your tuner picks what you want to look at, but AC is also at a low frequency, 60 hertz. That's traveling down the same coax as well. So I kind of look at it as a radio tuner that's out in the air on your radios, and that's a kind of an easy way to explain it for people who have a hard conception of having multiple frequencies on the coax.
Yeah, I think once you get your head around it, it's a little easier to understand. But initially, just understanding how power routing works um, and differentiating it from the RF path,
Yes.
this makes it easy. So thank you.
Yep. And a directional coupler is a similar way, except that it is an unequal power divider. This is the symbol of a directional coupler, where one of the ports, the output port, has a lower loss port, has more signal level, goes through the in, through the out, and the directional coupler taps off one of the signal with less signal level. There's higher loss going through the tap, and there's less signal level on this tap port. So this directional coupler is used in a network to split power unequally. Typical directional coupler values have 8 dB loss, 12 dB loss, or 16 dB loss in the tap port. So these are also bidirectional. And if you show the AC path on the directional coupler as well, you have this AC path, and you could see the same fuses that you can activate or deactivate independently on each port, the AC.
Now, in this instance, when we talk about a power divider, we're really talking about the RF power, right? Or the
Yes.
signal level. I've also heard the output legs called the through leg, which would be the out or the low loss leg, and the down
Yes.
leg, which would
Correct.
be the higher loss leg. Now, and on the upstream, these act as combiners, right? Because you have
Correct.
return signals coming back into the directional coupler, and then they're being combined on the one input or return output port.
Right.
Can you talk a little bit about the relationship between the insertion loss on the out and on the tap leg, or is that covered in a later slide?
Yeah, we can talk about that now, because the insertion loss, you can only split it unequally. So if you have more power going down the output, you have less power going down the tap port or the down leg. So a 16 dB directional coupler, or let's say here we have an 8 dB directional coupler. If an 8 dB directional coupler here, if there's 40 dBmV coming in, there'll be 32 dB coming out the down leg. So if you add the two together, you get 40 dB, subtracting 8 gets 32 dB out. And the out leg has 38 dBmV. That's 2 dB insertion loss through a DC8. But if you change this to a 16 dB directional coupler, that means less signals coming here. If there is a DC16, there's less signal through the out, but there is more power coming out through the output power. The typical insertion loss in a DC16 is 1 dB insertion loss from in to out. Then you would have a 39 dBmV output here. You have a higher output on this port, but a lower output here. So you can't create power in a passive device. So it's just how you split the signal. On a higher value directional coupler, you have more loss here and more signal level here and less signal level on the tap port.
Okay, so let's imagine a scenario where a technician has a coupler, a splitter, but sometimes the stickers on the faceplate are worn off, they get faded by the weather over time, and we don't know what the value is. We just know we have a coupler of some sort. What we could do is measure on the seizure assemblies on the input versus the outputs. And in a balanced two-way splitter scenario, right, our outputs would measure the same and be approximately 3.5 dB lower than the input.
Right.
However, if it were an unequal power divider or a directional coupler, we could measure the input against the outputs and actually determine what value the DC is, just through simple math.
Yes.